After doing a very in-depth look at polynomial functions in the last chapter, this chapter is going to be pretty much all about exponential functions and their inverses. So if you recall, a polynomial would look a very specific place where we would have the x's and the constants. So a polynomial function, actually I'll rewrite that as power, consists of a bunch of power functions, which would look like y equals x to the n. So in a power function, x is the base, and then we have this fixed exponent. So an exponential function is going to be kind of the flip of that. So that's going to be a function of the form f of x equals a to the x. So x is actually the exponent, and that's why we call it an exponential function. And that base a is going to be any real value. It doesn't have to be an integer. It doesn't have to be rational, but it does have to be positive. So any positive real number, basically. And so we're just going to investigate a couple of exponential functions. So some examples here. We have 2 to the x is probably the simplest one that's not 1 to the x, which does nothing. And then y equals a half to the x. So an example of one where the base a is smaller than 1. And so we'll just do a table of values here. No, I wanted that in black. And hopefully a little refresher again on some of those exponent rules that if you forget them, go have a look at section 3.1. Yeah, so I'm going to do my x and then 2 to the x, and then over on the right it'll be x and then a half to the x. So let's start, let's just make our way up from some negatives to positives. So if we start with the integers down below, 2 to the 1 is 2, 2 squared is 4, 2 to the 3 is 8, and then it's just kind of following patterns, right? If we go up by 1, it multiplies by 2, so if we go down by 1, it should divide by 2. And then, right, 2 to the negative 1 is the same as 1/2. That's that exponent rule of using the negative to flip. So 2 to the negative 2 is like 1 over 2 squared, so 1 over 4. And 1 over 8, right? Just we can divide by 2 as we make our way up that line. And then we'll do something similar here. And so on the right, so same idea that a half to the negative 1 is going to flip it and make it 2. A half to the negative 2 is going to flip it and then square it, so 4, and then 8. And then same pattern, anything to the 0 should be 1. A half to the 1 is itself. A half squared is a quarter, and a half cubed is a half by half by half is an eighth. And so we've got all of these values, and what we're going to do is put them in a graph. All right, so I've set up my tables. You'll notice I didn't put any negatives for my y values there. If you look at the numbers that I've drawn, they never get negative, right? And if I raise 2 to any power, it shouldn't ever really become negative. So yeah, so I didn't put any negative y's, but I do have negative x's, so I have those in there. And yeah, so we'll just plot all these points and connect some dots. So -3 and 1/8. So at -3, I just need like a super low little point there at 1/8. Negative, why don't I do the half first so I can sort of follow along what I'm doing here. -1.5 and -2 1/4. So it should be halfway down from the half, so probably about there. 0 and 1. And if you thought maybe it looked like a straight line with those first 3, you can see that -1 rises up a little higher. 1 and 2. And now you should be seeing they're definitely not in a straight line. 2 and 4. And 3 and 8. And so you can see what's definitely a pretty clear curve. It's a very simple curve. So it's just going to kind of try to draw this as best I can. Should go up like this. And yeah, so this should be the graph of y equals 2 to the x. And we'll do similar on the right-hand side. So -3 and 8 should be probably about here. -2 and 4, -1 and 2, 0 and 1. If you're noticing, the y values are exactly the flip of the y values on the other graph. A half, quarter, and an eighth. And so we can see that what we have here, same kind of shape. I'm trying to make this look nice, but it's hard to draw on this thing. And then if you're wondering what's going on towards the right there or the left on the other graph, so hopefully you'll believe me when I say that as our x values get bigger and bigger, so if I multiply a half to the 100, for example, it just becomes a super small number. It's never in the negatives, but it gets really, really close to 0. And it, like, every time I multiply by a half, again, it gets closer to 0. So what we end up actually getting on both the left side of the first graph and the right side of the second graph is a horizontal asymptote. So that's a really big feature for us. And remember, rational functions would always have the same horizontal asymptote on both sides. These exponential functions will actually only have the horizontal asymptote on one side, because on the other side, like if you look at the first graph for a, if I keep multiplying by 2 again and again and again, it's going to get bigger and bigger and bigger and like dramatically bigger. And so what's happening in that case is that the values just go towards infinity. They get larger and larger and larger. And so we have this like that end behavior on the right is that y goes to infinity. And same thing on the left here. We've got our y going up to infinity on the other side. So that's going to be a really key feature for any of these exponential graphs. It doesn't really matter what the base is. They'll always have one side that's flat and one side that has this infinite behavior. So really different than rational functions. But for the most part, other than that, they will be pretty standard curves. They'll be strictly increasing as we have on the left, or strictly decreasing as we have on the right, because moving 1 unit on the y equals 2 to the x graph, if we move 1 unit to the right, that's the same as multiplying by 2. So it should get bigger and bigger. On the right-hand side, if we move 1 unit to the right, you're actually dividing by 2. It's getting smaller and smaller. If you want to think of the language of symmetry, you might notice that 2 to the x is the exact mirror image of the half x. There's a relationship there. It's actually a horizontal reflection of each other. And so that's something else you might notice. This is a horizontal reflection of y equals 2 to the x. And that's because, oh, it looks terrible. Sorry about my writing there. Because y equals a half to the x is the same thing as writing 2 to the negative 1 to the x, right? 2 to the negative 1 is a half, is 2 to the negative x. We just use some power rules there. And that's the inside of the function. That would be the inside of our function has a minus attached to the x. That's a horizontal reflection. So a lot of ties with stuff that we've done earlier. Yeah, we'll do another question with the exponential. Just maybe look at the effect of a couple transformations. We really don't want to graph these with transformations, though. All right, yeah, so we're going to do a second question just to see what transformations are going to do. And then in the next video, I'll go over a faster method to graph these functions and having to use transformations, because if you remember, transformations are really tedious. So we're going to sketch f of x equals 3 to the x using a table of values, and then do some transformations to do this. -2 times 3 to the x minus 1 plus 5. So for a, now we'll have y equals 3 to the x. I'm going to do same table of values as before. I think the numbers will get pretty ridiculous pretty fast, so I'm not going to be able to graph everything here. So 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27. And as I make my way up, I'm going to divide by 3. So 3 divided by 3 is 1, divided by 3, divided by 3, divided by 3. Right? And so those numbers on the negative side should just be the flip of the positive ones. And I will sketch my graph. Oh yeah, I've got my axis. I did include the negatives this time because I'm going to do all the transformations on this graph as well. So I'm going to sketch this graph with the light blue so I can do all the transformations over top of it. So my y equals 3 to the x. Sorry, that 3 looks pretty terrible. And yeah, so I'm going to plot my points, 0 and 1, 1 and 3, 2 and 9, and I'm not going to be able to get 3, like 27 is going to be like up towards the top of that sentence there. And then I'll have a -1 and a third. And then this 9th is like pretty close to the x-axis. And 1 over 27 is going to be basically indistinguishable from the x-axis to me, almost. So what you see is a pattern that's very, very similar to what we had with the 2 to the x function. And I mean, all of these exponentials are kind of going to look the same. They're actually all just stretches of each other, but we can't really explain that yet. But they're all going to look the same. They're all going to be sort of flat on one side of the graph and then infinite on the other. And it's just like a single swooping curve. There's no weird bumps or curves or like curlinesses to it. It's just a very, very simple, strictly increasing or strictly decreasing curve. So that's going to be y equals 3 to the x. And so what we're going to do for b now is try to figure out our transformations, first of all. So if you look at this 3 to the x minus 1, that's almost f of x, but that's f of x with x minus 1 plugged in instead of x. So this is actually f of x minus 1. So hopefully you can kind of see that, right? If you plug the x minus 1 in here for x, we get the same thing. And so our g of x is actually just going to be -2 f of x minus 1 plus 5. So we've got 3 transformations there. So we'll draw them out. So that -2. And then I might as well I'll do these two separately, I guess. I'll do this one in orange since it's kind of already related to what's going on in there. And then in this dark burgundy color, I'll do my final graph of the plus 5. Right, and it's there's no b to factor out on the inside, so my b is 1, so I don't have to worry. The representation's okay. I should be able to just go ahead and do all of these left to right. So step 1, that's on the outside of the function. That will affect my y's. All of my y's will be multiplied by -2. All right, so that's going to be a stretch and a flip. Step 2, that is going to move everything to the right by 1. Remember, it's backwards to x on the inside. And then that plus 5 is on the outside of the function. It affects y, and it does exactly what it says it should do. It's going to go up by 5. All right. So we're going to track all of this. So this point at a height of 1 is going to go down to -2. A height of 3 is going to go down to -6. And that height of 9, I'm not going to be able to get on here. But I can, so that should be a third down to -2/3. A ninth down to whatever -2/9 ends up at. And a 27th is -2/27. It's going to be pretty close to 0. So it's going to look still really similar to the blue graph, just upside down. It almost looks the exact same, but if you're paying attention, you'll see it's a little bit, it's actually a little steeper than the blue graph. Yeah, you'll see some things that didn't change here. That stretch did not change the fact that the heights of the curve get really, really close to 0 as we move to the left. So this action here does not move the horizontal asymptote. that's something that's really important to pay attention to. The infinite behavior, so instead of going up to positive infinity, it now goes down to negative infinity, but it's still that same kind of just really simple curling curve without any weird behaviors to it. So the blue one is going to move everything to the right by 1. So this point's going to go over here, over here, over here, probably about there. It's really hard to tell what's actually going on the left because we have this flat line that represents the horizontal asymptote, and we're just taking that flat horizontal line and shifting it to the right along itself. So it's not, it's like on a track basically. It doesn't really leave that track. And so it's not changing the horizontal asymptote at all either. And so we end up getting basically this orange graph. So this does not move the horizontal asymptote. And then finally, we just have that one last thing, shift everything up by 5. So I'll get a negative 2/3 is going to come up to just under 4. This one is at negative 2, so it's going to go up to 3. This one's at negative 6, so it's going to go up to negative 1. And so this one was at what? I don't even remember what that is, so I'm going to just eyeball it. So it's going to go, if I go up to 5, which is where the 0 moves to, and it needs to go down a little bit. Oh, I think I have that first point in the wrong place. Yeah. So I'm going to redo that first point. So that's negative 2/3. So that should go up to 4 1/3, which is actually right about here. Yeah, that looks about right. And so this one should be negative 2/9, which is close to a quarter. And so it's going to go up to about here. Hopefully you can kind of believe me that they're all just going up by 5. And so we should get something like that. I was hoping to hit that point a little better, but yeah, this. And then hopefully you'll kind of believe me that originally we had this horizontal asymptote that went along y = 0. So I'm just drawing it with red here. And as we move to the left, all those first 3 curves, the blue one, the orange one, and the pink one, they all get really, really close to 0 the further left we go. And so now if we take all of those points that have a height very, very close to 0 and add 5 to them, we should now have a bunch of points that are actually all very close to 5. So what that shift up does is it actually moves the horizontal asymptote up by 5. So that's actually going to be one of the pieces that we can use to do the graphing later. But basically the key thing that we're seeing from these transformations is that no matter what kind of numbers we throw on top of an exponential function, we still do get a very, very simple curve where one side clings to a horizontal asymptote, and then the other side of the curve is going to either go like up to infinity or down to negative infinity. So all of these curves are going to look pretty similar. It's just a matter of like how we get them down. So that's going to be it for the math side of exponential functions. We will do a lot of applications, I think, later on with this. Exponential functions show up all over the place in all different kinds of math in the real world. The typical examples that you'd go over for a math course are going to be a lot of investment math uses exponents. Like when you're accumulating interest, you tend to get a multiplier on the previous value rather than just adding something, which would be a linear model. Yeah, so any sort of financial math is usually exponential functions. And a big one would be, the big one that has obviously been talked about a lot because it is the summer of, well, fall now of 2020. We've talked a lot about epidemiology. Basically, it's the growth of a virus or a bacteria. Those all do follow exponential models. And you've probably heard things like the R value being thrown around and words like that. They all have to do with these exponential models. So it's obviously super, super relevant for current events. And if I choose to reuse this video in future courses, it's obviously going to date the video. But yeah, exponentials are basically the driving functions for every single thing that naturally occurs in the real world. There's an exponential function behind them, like everything. So they are definitely the most useful function to know about. Linear ones are nice because they're straight lines, but linear functions don't happen unless we force them to happen. Exponents are where it's at. All right.